How are you doing? This is Mike here, and in this video we're actually going to evaluate some volume. So if you've watched some of the past videos that we've done, we've been looking at how to calculate areas, but now we're going to three-dimensionalize these objects, and we're going to rotate them about an axis, whether or not be the x-axis or the y-axis, or maybe one of the vertical or horizontal lines, and then we're going to determine what kind of volume is made. There are different methods of which every one of these problems can be evaluated. I'm not going to cover every method, but I'm going to cover what I see most frequently. If you're taking calculus with me, then you're going to realize that I am not method heavy. I just like to be able to calculate the problem's question simply and expeditiously, and there are some methods that are more effective than others. So with that being said, let's go ahead and determine how to find the volume of this solid. So here we have we have several curves. We have y equals to x squared, so we have a parabola that opens up. We have the line x equals to 0. We have the line x equals to 0. So this is a vertical line. And then we have the line y is equal to 4. This is a horizontal line, and then we revolve this about the y-axis. So the first thing I like to do with any of these types of problems is just to give myself an idea of what I am working with here. So these are not perfect depictions. This is the parabola y equals to x squared. So I like to use a lot of space. I want to give myself a lot of room, and this helps me tremendously. Then I have the line x equals to 0, so I'm going to do that in red. So x equals to 0 is going to be this vertical, horrible. So the line x equals 0 is going to be a vertical line that runs right down that y-axis. So hopefully we can all see that. So this is x equals to 0. And then in blue, we're going to do the line y equals to 4 here. So we got y equals to 4. So where do we have an intersection? So some people might say, well, this is all an intersection. No, this is not. So we're going to look to the right of the y-axis and above the x-axis. So here we have now found this enclosed area right here. So now what we're going to do is that we're going to take this y-axis and we're going to rotate it. So I like to put a little corkscrew up on top indicating that I'm going to rotate this. So I am going to rotate this continuously, and by me rotating this, I'm going to have a bowl. We're going to have a bowl, some bowl. I'm not going to get into the three-dimensional drawings of this because again I'm looking for the calculus. So so it does help me, but I'm just going to do a quick depiction, the best that I can do here. So we have this that looks like this, and it looks like this, rotated here. So we are going to create the opposite end. Looks like that. So that's horrible. So it looks something like this. But in the meantime, we're going to create this three-dimensional volume like this, like such. So it creates a bowl, and again, that's why I wasn't so big on wherever we ever picked the first enclosure, the second enclosure, because we're going to get the exact same thing. So hopefully we can see, we get this bowl. This bowl is going to have a radius that is changing depending upon where we draw this radius, but again, we're going to have a sort of a bowl. So now how do we evaluate this? I know that I like to first of all find some very key points. So I recognize here that I have the beginning at the origin, which is going to be 0, 0. And then over here at the farthest point away, maybe I'll do this in a blue color, I recognize that when y is equal to 4, that x is equal to 2. So, oh no, how'd that happen? So, for some reason, it just likes to delete my drawings. So we have 2, 4. So how can I evaluate this? I know that for me, I look at this and I see a radius. So I'm going to draw this radius in red, and this radius exists from the y-axis, out to the curve. So we have a radius here that exists from the y-axis out to the curve, and this tremendously makes this a lot easier for me because I know that I want to use the disk method to evaluate this volume. So if I want to evaluate using the disk method, this is going to be a nice way to evaluate this. This will be the integral, so the volume will be integral. So from some value to some other value of pi times some radius squared, and then we're going to integrate this with respect to something. But it helps me to figure out which way is actually easier to evaluate. So I know for me, I see this length of the radius, this is just going to be a value of x. This value is just going to be a value of x because it can change. It can be this value from here to here. It can be this value from here to here. And every time I change that radius, it's just going to be a different value of x. So my radius is a value of x. We know that x will be equal to square root of y. And we don't have to worry about the plus or minus here because we're looking at the curve and it's rotating around the y-axis, and we're only going to look at the positive portion of the solution. So if my radius is perpendicular to my axis of rotation, so notice here the radius is perpendicular, so I'm going to even show that my radius is perpendicular to the axis of rotation. I use the disk method. If my radius is defined in terms of x, I'm going to integrate with respect to y. So I'm going to integrate with respect to y. So all my variables must be defined in terms of y. So that's just the nice thing about the disk method. I use the disk method. My axis of rotation is y. My radius is defined in terms of x. Therefore, I'm going to integrate with respect to y. So let's go ahead and tackle this. My lower bound with respect to y is a value of 0. My upper bound with respect to y is a value of 4. I keep my pi, but since I'm integrating with respect to y, I'm integrating with respect to y. I'm using the disk method. My axis of rotation is the y-axis, so I'm integrating with respect to y. I have to redefine x in terms of y, so I'm going to integrate square root of y squared dy. So this is a square root of y squared dy. So again, let me articulate what I was thinking. My axis of revolution is the y-axis. I define my radius perpendicular to my axis of revolution, so I define my radius perpendicular to the axis of revolution. It must be defined perpendicular to the axis of revolution. And since I am rotating about the y-axis, a vertical line, I'm going to integrate with respect to y. Okay, so now I'm going to pull that pi out as a constant, integrate from 0 to 4. Square root of y quantity squared is just a value of y, and this is going to be dy. Integrating a value of y, we're going to have pi times y squared, and we're going to leave that 1/2 out in front, and it's going to be evaluated from 0 to 4, and this gives us a really nice integral, so we're going to have pi over 2, and this is going to be 16 minus 0, which just gives us a value of 8 pi, So hopefully this question makes some sense. The keys that I look at are first drawing the problem out. That's a huge step. Finding what we're evaluating, rotating about the axis of rotation, define your radius perpendicular to your axis of rotation. And since this is just screaming to me disk, and again, when we think about disk method, I'm creating little disks of a small dimension of a width dy, and I'm summing all those individual disks. So that's more theoretical based. I'm not going to get into how the disk method works, but this was definitely a question that screams disks.